This is Unit 2, Lesson 1, Linear Systems. The objective, students will set up linear systems of equations and solve them by graphing. So let's start with the setting up part. Here's a real-world type problem. You want to open a checking account. Bank of America charges $3 monthly fee and $40 per check. Capital One charges a $5 monthly fee and 20 cents per check. Write one equation to represent the bank's total cost as a function of a number of checks written, and that's going to be X. So Y is going to be the total cost, and X is going to be the number of checks you write. So you can see that we always have Y equals, and it's going to equal the rate times X plus the initial cost. So for Bank of America, the rate is 0.4 because it's 40 cents a check, X, and the initial cost for Bank of America, that is the cost if I didn't write any checks, would be 3. And for Capital One, this is a separate equation. For Capital One, Y is going to equal 0.2x because the rate is 2, point is 20 cents, plus what's the cost if I didn't write any checks? It would be 5. Now by setting that up, by writing those two equations, you have just set up a system of equations. So linear systems, otherwise known as linear systems of equations, are sets of linear functions. For each function in the system, we're going to understand that the variables are the same throughout each function. So if I know Y for 1, that's supposed to be Y for number 2. If I know X for the first one, that's supposed to be X for the second one. So that's the linear system we just set up there. So whatever I say X is, then that's the X for all of the equations. Whatever I could say Y is, then that's the Y for all of the equations. Now there's 3 possible outcomes of these system of equations. Potentially they could have no solutions. There's no X and Y that's the same in both equations that makes both equations true. Or it could be infinite solutions. There's an infinite number of X's and Y's that you could put in that makes both of those true. So if it's no solutions, we say it's inconsistent. If there's infinite solutions, we say it's dependent. And if there's only one solution, only one X and Y that work in both of the equations, then we say that it is independent. So let's find out how we can solve these two equations and find out if there's one X and Y that works in both of them. And the way I'm going to do that is by graphing. But before I graph, because rates of changes are drawn on the graph by using rise over run, it's better to write the 0.4 and the 0.2 as fractions. So if I convert 0.4 to a fraction, it becomes 4 over 10, which simplifies to 2 over 5, as I have written in the blue equation. And if I simplify 0.2, that's 2 over 10, which simplifies to 1 over 5, as written in the red equation. So I'm going to put that on a graph. And again, the y-axis of this graph is the total cost, and the x-axis of each graph is the number of checks that you write. So first I'm going to graph the blue graph. The first thing I do when I put a graph is I make a mark where the initial value is. So if I wrote 0 checks and the x-coordinate is 0, then the cost is going to be 3. So I put a dot at 0, 3. Now from that dot, the rate of change is 2 over 5. So I go up 2 spaces to 5, and I go over 5 spaces from there. 1, 2, 3, 4, 5 is going to take me to 5, 5, and I put a dot there. When drawing linear equations, once you have 2 points, you are finished. I'm sorry, you should say you are nearly finished. You just connect the dots with a straight line using a ruler, and that's the graph of that equation. So any x that's on that equation, any point that's on that equation gives you an x coordinate and a y coordinate. Those x coordinates and y coordinates will make that equation true. For instance, if I wanted to know what y would be if x equals 10, I would simply go over to x being 10 right there and go straight up until I hit the line, and at that line y is 7. So without even writing it in, I know that one solution to that equation is x equals 10, y equals 7. Okay, moving on. Now I need to graph the red line. And on the red line, my starting value is 5, and from there I count up 1 and over 5. So that gets me to 6, 5. I draw the line, and I see that all the potential solutions for the red equation are on the red line, and all the potential solutions for the blue equation are on the blue line. Anything that's not on either of those lines will give you a false statement for the equations, for both of the equations. Anything that's on the blue line and not on the red line will give you a true statement for the blue equation but a false statement for the red equation. And any point that's on the red line but not the blue line will give you a true statement for the red equation and a false statement for the blue equation. There's only one point on this entire graph that gives you a true statement for both equations. And that is the point we referred to before. That is the point 10, 7. So the solution to the system is 10, 7. That's where the lines intersect. And we can check this by plugging them in to the original equations. So if I plug in 10 for x, it should equal 7 for both equations. So 0.4 times 10 is 4, plus 3 is 7. So that works for the first equation. And 0.2 times 10 is 2, plus 5 will also give us 7. So both of those equations work properly. Now, of course, they won't all be this nice. And what I mean by that is sometimes you won't have y equals as the equation you're trying to graph. You'll have x plus y equals 2, or 2x plus 4y equals 12. And that's going to involve a step first of isolating the y. So what we have to do before we can graph these equations is we have to get them into a y equals type format. For the first equation, that's relatively simple. All you have to do is subtract x from both sides, and that's going to give us y is equal to negative x plus 2. So if I look at that equation, the initial value is 2 and the rate of change is negative 1, which is of course negative 1 over 1 if I change it to a fraction. The other one is a little trickier. First I have to subtract 2x from both sides. That gives me 4y equals minus 2x plus 12, so I have to divide not just the 4y by 4 to isolate the y, but everything by 4. So 4y divided by 4 is y. Negative 2x divided by 4 is negative 2 over 4, which is simplifies to negative 1/2 x plus, and then 12 over 4 is 3. So y is equal to negative 1/2 x plus 3. Now I have equations that I can graph. I'm going to graph y equals negative x plus 2 in red, and y equals negative 1/2 x plus 3 in blue. So the first thing I do is I graph the initial value. So if I plug in 0 for x, 0 plus 2 is going to give me 2. So on the y-axis, it's 2. That's the initial value. From there I use the slope, and in this case the slope is negative 1, which as a fraction is negative 1 over 1. So that means I go down 1 and to the right 1. Now I have my 2 points, and I use a ruler and connect them with a line. For the blue graph, my initial value is 3. My rate of change is negative 1 over 2, so I go down 1 and over 2 from that first blue point. That gives me a second blue point. I connect them, and there we have it. Remember, every point on the blue line, even the ones that didn't mark, is a potential solution, is a solution to the blue equation. Every point on the red line, even the ones that aren't marked, is a solution to the red equation. There is only one solution on this graph that is a solution for both equations, and that is the point negative 2, 4. So in this equation, for this set of equations, when I solve it, the only x is negative 2 and y is 4 is the only solution that works in both of the equations. Here's another one to try. We have y equals 2x minus 4 and y equals 2x plus 6. Now fortunately for us, it's already in y equals format. So the first equation, the red equation, we start at y is negative 4. We go up 2 over 1, because if I turn 2 into a fraction, it's 2 over 1. I put the line there. The other one starts at 6, again is up 2 over 1. So I put the line there. Now those lines have the same rate of change. They do not cross each other on the graph, and since they have the same rate of change, then they have to be parallel. Those lines will never get closer to each other and never get farther apart from each other. So they will never cross. If the lines never cross, then there is never going to be any point that is a solution to both equations. So there's no solution, and that is inconsistent. Having the same rate of change is a dead giveaway. If they have the same rate of change, then the problem is never going to be independent. You're never going to get one solution if you have the same rate of change. The only thing you can have is an inconsistent set of equations or a dependent set of equations. Now, the difference between an inconsistent and dependent set of equations is an inconsistent will have different initial values, whereas just like this one, you have -4 and +6. A dependent set of equations will have the same initial values. So you can tell if something's inconsistent, independent, or dependent without having to draw the graphs if I pay attention to the rate of change and the initial value. Here's the homework for today. It's page 28 in the book, numbers 3 to 24 in threes. Now that's a new concept. When I say in threes, I mean you do every problem that's divisible by 3. So you start with 3, and then do 6, and then do 9, and then do 12, and so forth and so on, until you get to number 24. Good luck on the homework, and I'll see you next time in class.